Hello students, in lecture 13 of your course Advanced Calculus and Special Functions, and the Advanced Calculus part, in this lecture we introduce you with the Young's theorem, Schwarz theorem, and then certain examples related to these theorems. First, the statement of Young's theorem, that f be a function of two variables fx, fy be differentiable at point AB of the domain of definition of f, then this second order partial derivative of f xy AB at point AB is equal to f of yx at point AB. That means if you change the order in the second order partial derivative, the value of this derivative is equal at a certain point AB, provided the condition is satisfied. What is the condition? That the first order partial derivative of f with respect to x and with respect to y must be differentiable at point AB of the domain of definition. So this is the statement of Young's theorem. Now we have already discussed the concept of differentiability of a function. So again we recall the definition here. When do we say that a function is differentiable at a certain point? And particularly here we are discussing the functions of two variables. Let xy be any point, and x plus delta x and y plus delta y be two neighboring points in the domain of definition of f. The change delta f in the function as the point changes from xy to x plus delta x and y plus delta y is given by this delta f equal to f of x plus delta x, y plus delta y minus f of xy. In certain books it is also given like this, that we write delta f is equal to f of x plus h, y plus k minus f of xy. The function f is said to be differentiable at point xy if the change delta f can be expressed in this form. This is the important equation here. F is said to be differentiable if it can be expressed in this form. Or alternately, I can write this equation in this way, because delta f is equal to this thing. So I can write it here, that f of x plus h, y plus k minus f of xy. This is the thing, in place of delta f we are writing it, and that is equal to, we write it as a delta x plus b delta y, and plus, in place of this delta x we can write here h, because we are making the change h in the variable x and k in the variable k. So that is why in place of this we can write h, and this is phi. Phi is the function of course h and k. In place of delta x we can write h and k. So simply we are writing here h phi and then k psi. Of course, this phi and psi, these are functions of the variations h and k. So here in this equation, a and b are constants independent of delta x and delta y, and phi and psi are the functions of delta x and delta y tending to 0 as delta x delta y tends to 0 simultaneously. So the first part, this part, because we are saying that delta x delta y tends to 0 simultaneously, and this phi and psi tends to 0. In that situation this part becomes 0 and we are left with only this part, and this part a plus delta x and b plus delta y is called the differential of f, or we simply denote it by df. Now this is not delta f, now it is df when you have applied the limits tending to 0 for delta x delta y. So you are getting this equation here. So now this df is called the differential, and in fact here a is nothing. A is in fact the partial derivative of f with respect to x, and b is nothing but the partial derivative of f with respect to y. So this is the fact you need to keep in mind for the purpose of numerical problems. And a means here in this definition fx and b means fy, partial derivative of f with respect to y. So if this type of condition is satisfied here, then we say that function f is differentiable. Okay, so from 1 you can also see when this tending to 0, this part goes to 0, and the function f is continuous at point xy. Thus every differentiable function is continuous. This is also there. So now we are coming to the definition of Schwarz theorem. The statement at the statement of the Schwarz theorem, if this f subscript x exists, means the partial derivative of f with respect to x exists in a neighborhood of the point AB of the domain of f, and fyx is continuous at point AB. This is continuous at point AB. Then this second order partial derivative fxy exists and is equal to fyx at AB. In fact, in this case also, fxy AB is equal to fyx AB, provided the conditions given over here must be satisfied. So what are the conditions? First order partial derivative must exist with respect to x, and fyx is continuous at point AB. fyx is continuous at point AB. Only then you can say that fxy exists, right? So this is the statement, but one remark is there. If the conditions of Young's and Schwarz theorems are satisfied, then definitely the second order partial derivatives fxy and fyx are equal at a point AB. But if the conditions are not satisfied, then we cannot draw any conclusion here, because in that situation fxy and fyx may or may not be equal. So in order to focus, or in order to put further elaboration on this remark, we discuss here two examples. The first example is here. You see, show that for the function fxy equal to x square y square divided by x square plus y square, when xy is non-zero, and it is 0 when x equal to y equal to 0. Then in this situation, what we have to show for this function that fxy equal to fyx at the point 0, 0, even though conditions of Schwarz theorem and also Young's theorem are not satisfied. Fine. So first we are discussing here the condition of Schwarz theorem. In the Schwarz theorem, as you know, what is the condition? This first order partial derivative must exist at point 0, 0. And then we have to check the continuity of the second order derivative fyx. Fyx we have to check here. We have to check the continuity of fyx at point AB and the existence of this fx. So you see here, we find the value of fx, means first order partial derivative with respect to x at point 0, 0. In fact, by definition, we will write limit h tending to 0, and it will be 0 plus h comma 0 f of minus f of 0, 0 divided by h. Now this f of h0 from here, from this part, in place of x we'll write h, and in place of y 0. So ultimately the whole thing becomes 0, so we are getting 0. Similarly, if we find fy, this is also fy at 0, 0, it is also 0. Now when xy is non-zero, then fx, if we simply calculate from this part, we simply, by the conventional method, we partially differentiate this with respect to x, we get this type of expression, right? And for y, if we are differentiating, we are getting this type of expression. This is twice x4 is here, y divided by x square plus y square, and it's a whole square is there, right? Now we find fyx, means first You have already taken differentiation of f, partial differentiation of f with respect to y, and then you are again differentiating it with respect to x. But in fact, here is some reverse thing. You can also do like this. It depends on the notation what we are following. It should be uniform throughout. In fact, here first it has been differentiated with respect to x, and now we are taking the differentiation with respect to y. So that is why in place of f here we shall use f subscript x and f subscript x, and we are now further differentiating with respect to y. So that is why this will be 0 and 0 plus k, fx 0 0 but divided by k tend to 0. Now you have the value of fx here, and in this value you put x is 0 and y is k. So in fact the whole thing again becomes 0. So that means fyx comes out to be 0. Similarly, you find fxy at 0, that also comes out to be 0. So that way you can say fxy at 0 0 and fyx at 0 0 both are equal. So one thing is obtained, that if we are changing the order in the second order partial derivative, then their value at a point 0 0 are same. Now we want to check the condition of Schwarz theorem. In the Schwarz theorem, we require two things, that fx exists. We have already shown the existence of fx. Now we want to check the continuity of fyx at point 0 0. So let us see what is fyx. So fyx is this, means you first differentiate it with respect to x, and then with respect to y we get this expression from here. We already differentiated with respect to x, and then you again differentiate it with respect to y partially. You will get this expression here. After simplification we are getting this quantity 8x cube y cube divided by x square plus y square and whole cube. Now this is value of, in fact, f y x x y. Now when do you say that a function is continuous? The simple thing is that you want to check the continuity at point 0 0 of the function fyx. Then this limit xy tend to 0 0 fyx must be equal to fyx at 0 0. But you have already obtained that value of fyx at 0 0. This you have already obtained that this is 0. Now you want to check whether this limit comes out to be 0 or not. Let us see. Because you are approaching the origin point, the point 0 0. Let us approach this along the path y equal to mx, and when we put here y equal to mx and then apply the limit xy tend to 0 0, in fact this value not unique, it will depend on m. Therefore we'll say the limit xy tending to 0 0 f of yx is not equal to 0, and this is not equal to this quantity. So we can say that the function fyx is not continuous at 0 0, and therefore the condition of the Schwarz theorem are not satisfied. Conditions of the Schwarz theorem are not satisfied in this case, and despite of that the second order partial derivatives at a point 0 0 are equal. So this is in context of that remark. We are having one example. Now we again have one example. In this example we have checked the conditions of Schwarz theorem. Now we'll check the conditions of the Young's theorem. So now what do we require in the Young's theorem? In the Young's theorem we need to have the differentiability of fx, whether this fx is differentiable at 0 0 or not. Let us go back to the Young's theorem. What do we require? That the very fx and fy must be differentiable at the point AB. So first we are checking in this example. First we are checking the differentiability of the function fx. Check the differentiability of fx. So in means that definition of differentiability, in place of f we will be having this f subscript x. Fine. So we find fxx, that means we are again partially differentiating fx with respect to x. So you get value 0 here. Also fx, you know this fx is differentiable at 0 0 if the definition is, as I told you in the definition of differentiability, here it is f, but here you are checking the differentiability of fx, that is why we are taking fx hk minus fx 0 0. Then in fact, if here we use f, then here it must be fx and here must be fy, but here we are already using fx, so it will be fxx and it will be fyx at 0 0. In fact, this is a according to the definition of differentiability, and this part is b according to the definition of differentiability. K h phi plus k psi, and phi and psi are the functions of h and k. Fine. So here we simplify what is the value of fx hk. You have already calculated value of fx is this one. The value of fx is this one here. So here x is h and y is k, so we are getting this term here. Okay, fxs is 0, and also we have calculated fyx is 0. So we are left with h phi plus k psi, where phi and psi tends to 0 as hk tends to 0 0. Now if we put h equal to rho cos phi cos theta and k equal to rho sin theta in this equation, consequently we get this value 2 cos theta sin 4 theta cos theta phi sin theta psi. Now when hk tend to 0 0, it is the same thing when we can say that rho tends to 0, and in that situation theta is an arbitrary number. Now proceeding these limits, what happens when you take hk tend to 0 0, then according to definition of differentiability, this phi and psi also tends to 0 0. That means this 0 and this 0. So ultimately in right hand side we will be having 0, and in left hand side we will have this expression, so we get this quantity. Now for the arbitrary value of theta, if theta is arbitrary, I can take anything. I can suppose I take theta is equal to pi by 4, means 45 degree. So you know cos 45 is 1 by root 2, and sin theta sin 45 is also 1 by root 2. 1 by root 2 power 4, 1 by root 2 means in total 1 by root 2 power 5 and 2 equal to 0. So this is not true. So for arbitrary value of theta, this equation cannot hold. Yes, it can hold for particular values of theta. For example, you take this theta equal to 0, then it is true. And if you take theta equal to pi by 2, this is also true. But for arbitrary value, this equation is not true. And hence, fx is not differentiable. How this equation we have obtained? By consideration that we have fx as a differentiable function, but we are not getting a true result. Therefore, fx is not differentiable at the point 0 0. Similarly, we can show that fy is not differentiable at point 0 0. Thus, the conditions of Young's theorem are not satisfied. But we have already shown that fxy at 0 0 and fyx at 0 0, these are equal. Now come to the next example. In this example, you see, show the function this xy into x square minus y square, x square minus y square divided by x square plus y square when xy is non-zero, and the value of function is 0 when x and y both are 0, means f0 0 is 0. Does not satisfy. This function does not satisfy the conditions of the Schwarz theorem, but fxy at 0 0 and fyx at 0 0 are also not equal. So we can show here, we can, as the procedure you know how to find fxy at 0 0 and fyx at 0 0, we can obtain it. It is very simple calculation. We will obtain that fxy at 0 0 is 1 and fyx at 0 0 is minus 1. So definitely these two are not equal. Now let us check the condition of the Schwarz theorem. When xy is non-zero, we have the first order partial derivative with respect to x. Fx means we get this value, and this is the expression. And then further we differentiate it with respect to y partially, we get value of fyx equal to this. Now, if we approach, because for condition of the Schwarz theorem, we have to prove that this fyx is continuous at point 0, 0. So for that, we have to find the limit of xy, f of yx, xy. So when we find the limit, so when we approach the origin along this path, definitely this will not be unique, but we have obtained that the value of fyx at 0, 0 is -1. So these two things will not be equal, and hence we'll say that fyx is not continuous at 0, 0. Therefore, we can say the condition of Schwarz theorem is not satisfied, and the two partial second order partial derivative fxy and fyx are also not equal. So these two examples are justifying this remark here. If the conditions of the Young's and Schwarz theorem are satisfied, then it happens. But if conditions are satisfied, then we cannot draw any conclusion whether these are equal or not. So we have considered one example in which conditions are not satisfied but these are equal, and the second example was for the case when the conditions are not satisfied and that these two derivatives fxy and fyx are also not equal. So that is it about this example, about this lecture. Thank you.